Welcome to our Ultrafast Laser Lab. In our Ultrafast Laser Lab, we are using a commercial femtosecond laser, and also we are developing new types of ultrafast laser in the infrared regime. The purpose of this Ultrafast Laser Lab is to investigate high field physics and to investigate ultrafast phenomena. Here you can see a titanium cipher oscillator which feeds all the ultrafast experiment down the road. This oscillator is a very broad oscillator, and it also feeds the ultrafast infrared laser that we are developing here. We are doing a few experiments with this ultrafast laser. Some of them are high harmonic generation. We are investigating resonance high harmonic generation and the underlying physics below this unique high harmonic generation phenomena. Unlike a regular high harmonic generation, where we have a typical spectrum of odd harmonics with a plateau that we call the plateau region, and we don't have any structure of the atomic that we are using. We can use neon, we can use argon, we can use even molecular gas, and with all these gases we have the same structure of the harmonics without any signature of the structure of the atoms that we are using. In our case, we are using evaporation of some metallics, and in that case we can see one of the harmonics which is pronounced with respect to the neighboring atomic, and this is a signature that we have some resonance involving in this process. Very interesting, this resonance is lying above the ionization level, and therefore this is a signature of multi-electron excitation, and what we want to study here is the dynamic of the multi-electron interaction and how they involve in this resonance harmonic. Another thing that we are doing here, we're taking this very broad spectrum of the oscillator, and we want to use it to generate ultrafast laser in the infrared, with the goal to extend the energies of high harmonics into the kilo-electron volt, and also to investigate harmonics in solids. So what we are doing here, we're taking the very broad spectrum of the oscillator, and we can mix the red part of the spectrum with the blue part and generate a seed in the infrared. So here you can see that we are mixing the red part and the blue part of the spectrum in a nonlinear crystal, and generating the seed in the infrared at around 2.5 micrometer. And then we are pumping with this home-built thulium-ELS laser a unique laser material called chromium zinc selenide. This chromium zinc selenide is a very new and unique lasing material. It can laser in a very broad spectrum, and we are seeding this infrared laser into this chromium zinc selenide gain medium. We have a multipass amplifier here, and we can amplify this few nanojoule seed up to 1 millijoule pulse about 50 femtosecond pulse. With this very unique infrared laser, we are doing a few experiments. One experiment is to generate electron-induced recollision, but in energies that exceeding 1 kilo electron volt. And we can use this electron to tunnel it out from the atom, accelerating it in the laser field and recolliding it back with the atom. Because of the unique wavelengths that we are using here, we can have very high energies of this recolliding electron. We can return it with more than 2 kilo electron volt, and we can excite inner shell electron. This is a very, very unique experiment that only we are doing here, and we can show that we can excite electron from the inner core shell of neon, krypton, and so on. So it gives us a unique tool to investigate the dynamic, the very ultra-fast dynamic of inner shell electron. Another thing that we want to do with this laser is to generate harmonics in a semiconductor. This is a new field that now people start to investigate since 2011. Very much the same that we are doing harmonic in gases, we can do harmonics in solids. But in solids we have more knobs to play with, because we have the symmetries of the solids, and we have the different band gap of the solid and the band structure of the solid. So the physics is much more richer of the harmonic in solids than harmonic in gases.